Yeah, welcome
Okay.
everyone to the first in-person seminar, CSDPIC seminar in over 2 years. We're really excited. Sorry about the technical difficulties. Yeah, we have to move. If anyone is interested in joining us, we are in 20043 downstairs, not 20001. We are honored to have Professor Onur Mutlu here. Professor Mutlu is a professor of computer science at ETH Zurich, and he's also a faculty member at Carnegie Mellon, where he previously held the Strecker Early Career Professorship. His current broader research interests are in computer architecture, systems, hardware security, and bioinformatics. A variety of techniques he and along with his group and collaborators have invented over the years have influenced industry and have been employed in commercial microprocessors and memory storage systems. He obtained his PhD and MS in ECE from the University of Texas at Austin, and BS degrees in computer engineering and psychology from University of Michigan, Ann Arbor. He started the computer architecture group at Microsoft Research in 2006 and held various product and research positions at Intel, AMD, VMware, and Google. He received the Outstanding Research Award in IEEE High Performance Computer Architecture Test of Time Award, a bunch of things. IEEE Society McCluskey Technical Achievement Award, the Morris Booth Award, and the inaugural IEEE Computer Society Young Computer Architect Award, as well as Intel Career Faculty Award, US NSF Career Award, and the CMU LA LAD Research Award, as also faculty partnerships from various companies and a healthy number of best papers and topic recognitions at various computer systems, architecture, and security venues. He's an ACM and IEEE fellow and an elected member of the Academy of Europe. So we are really excited to have Professor Onur Mutlu talk about his extremely exciting work, which has completely changed the industry as you know it. And he is talking about the security aspects of DRAM, the story of RowHammer.
Okay, thank you very much, Karthik, for the nice introduction. First of all, can everybody hear me? See me?
I don't know what see. Yeah, I can.
Crackling noise. Okay, interesting. Is there a way to fix it, or should I wear something?
Maybe I'll just get rid of my audio. Maybe.
Okay.
Switch audio disconnect. You can just even like. Can you also try disconnecting audio?
I think my audio is connected. Okay. Should I disconnect or mute or? Oh, okay, because the room is connected. How about right now?
Can you hear? Is it better? Is the audio better? No, cannot hear.
Okay, you cannot hear.
Okay.
Okay, unmute then. How about right now? Oh, okay.
No,
Sorry.
there is some noise apparently on the line.
Is it any better?
Do we still have the noise online?
Is it because where my computer is sitting or? Okay, yeah, I can do that.
Yeah, that might be the.
Can you guys Slack me the?
Yeah, I disconnected. But...
the WebEx link?
Oh,
I'd like to listen.
Yeah, sure, that would be.
Yeah, maybe we can listen. Sorry about this. And my screen's also a bit weird. I don't know why. It was okay a little bit earlier. Let me try one more thing.
Another quick question would be okay if you record the talk?
Yeah, perfect, okay. Fine, no problem. Yeah.
I'll begin that one.
Yeah, I don't know why I see this one, but hopefully WebEx people don't see it.
Okay, I think it looks good. WebEx looks good.
Okay,
All
yeah.
right, I'll join and see how.
Sure.
Okay.
Thank you.
Okay. Hopefully the sound is bearable, right? Is that okay? Should I proceed?
I think you should go ahead. The sound is a distraction, but we can hear your voice clearly.
Okay, that's. I'll try to also speak up. Hopefully, and let's see how it goes.
Yeah, I'm starting the recording for CSDPIC seminar by
Okay.
Thank you.
Okay. Okay, thank you very much, everyone, for attending remotely. Okay, and in here, it's a great pleasure to be here. I have not been here for 3 years, I think, and this is one of my first in-person talks. So I'm going to talk about RowHammer. This is a topic that I did not really discuss in much detail at IBM before, but we have some interesting results recently, and I wanted to share it. And Pradeep and others thought it was a interesting topic, so let's go into it. And feel free to ask questions. I mean, I can stay as long as needed. I have a lot of slides also. We don't have to cover everything.
That's the usual.
Yeah, usual. Exactly. We have usual disclaimers, let's say. But hopefully we'll get to some really interesting things toward the end also. Okay, when I talk about RowHammer to students, I basically give a picture of this bridge. This is the Tacoma Narrows Bridge. It doesn't exist anymore because a bit flip happened to it. And in 1940, it basically crashed. It became a reliability, safety, and security problem. And clearly, this is infrastructure, important infrastructure. I'm going to show you later bridges, including from 2022, things like this. And we deem this as critical infrastructure, but our computing infrastructure is much more important. We're going to bet our lives on our computers for a long time. And we should be much more careful about bit flips happening in our computing infrastructure. I also show this picture where people are constructing this rod, and a minute later, they may not be very happy if a bit flip happens on this rod. And these things actually exist. I'm going to, in slide 140 or so, we'll see another bridge that is in a town that I used to live in. And if a bit flip happens, 1 minute later, you may not be very happy, basically. So I think of security based on this as about preventing unforeseen consequences. This is, of course, a very general, broad definition. But if we can achieve at least a good fraction of this definition, then we can do a lot better than today. Okay, with that backdrop, what is RowHammer? It's the fact that you can predictably induce bit flips in commodity DRAM chips. And at the time we studied this for the first time, we found out that more than 80% of the tested DRAM chips were vulnerable. It's going to be very similar today, actually. It's getting much worse. And it's what's interesting to me is it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. This is really the first big connection, in my opinion, that we have seen between reliability, hardware reliability, and widespread security issues, let's say. And as a result, people are writing articles that look like this: forget software, now hackers are exploiting physics. And I like this because it's really a nice, high-level connection to RowHammer. It's really about physics in the end. And we were very interested in studying technology scaling problems in main memory, in DRAM, for a while. And this was a paper that we presented in the International Memory Workshop. In fact, I gave a tutorial at the International Memory Workshop yesterday, remotely, from my hotel room in Pittsburgh, about RowHammer. But this was an invited talk that we delivered, where we talked about basically these memory scaling issues getting much worse going into the future, and we should really do something about it, including reliability issues, latency issues, etc. At that time, we were working on RowHammer, but we had not published the RowHammer paper, so we did not talk about this over there. But we were gathering a lot of data, and I'm still very interested in gathering a lot of data. And basically, the issue is we have technology scaling issues in everything. And DRAM is particularly interesting because DRAM is the memory that's used to build main memories of almost all computing systems that we have today. It's a charge-based memory, and clearly it was invented here, right, at IBM in 1960s. It stores charge in a capacitor, and capacitor must be large enough for reliable sensing, and the access transistor must be large enough for low leakage and high retention time. And as you reduce the size of the cell, both of these properties become difficult to maintain. And you get into a lot of noise issues, reliability issues. And we were very interested in looking at a lot of those reliability issues, essentially. So let's talk about some of them. First of all, we did the study with Facebook around 2013, 2014. We published this paper in DSN in 2015. Essentially, we wanted to, we analyzed all of the memory errors that Facebook experienced in their production data center servers running real workloads. This is a lot of servers, and this is very interesting, statistically significant data. I'll give you one data point over here in this picture. This picture basically shows a correlation between the chip density, DRAM chip density that's employed in the server, and the relative server failure rate that you get. And if you really want to understand how we compute the y-axis, you need to read the paper, you need to normalize things. But the takeaway is, as chip density increases, server failure rate also increases because you get more memory errors in denser chips. Why? Because cells are smaller and cells are closer to each other, and they're much more vulnerable to noise. And this is, I think, shown in other papers by other people, also like AMD or National Labs, for example. And server failure rate is just crash, or? So yes, it's errors also, uncorrectable errors, correctable errors. We include the correctable error. We don't include the uncorrectable. We don't include all the correctable errors, but correctable errors that lead to, let's say, correctable error storms that may lead to hangs.
What about silent data?
So that's something we are not able to completely include. So there may be actually more than what we show over here. That's a great point, basically, because we're not able to test it, and at least in this configuration that we have.
And you have like software checkers on top of this, or does that also include those kinds of errors?
Exactly. If the software checker catches something and stops the world, let's say, for some time to analyze what's going on, yes, it includes those.
And what about ECC corrected ECC errors for this?
So we have that in the paper. We discussed the amount, but we don't include in the failure rate. It's not really a failure for us. If it's corrected, it's not a failure, basically. It has to either hang or like corrupt some data or basically become unresponsive, let's say, or crash. Yes. Okay. So this is also fascinating, certainly. I'm happy to discuss this, and I'm really interested in doing studies like this also going into the future. We're doing some studies with like some.
There's a request in the chat.
Breaking up significantly to that online. Are you using the audio in the room or the audio from the PC?
So that's a great question.
I think you're in the room, right?
But how do I switch to the room? Because
They want them to can the audio person.
I don't know how to
John
switch to
is,
the room.
Yeah, I see John. John, is it currently on the room audio, the PC audio? Yeah, I just see John actually. He joined in.
So they told me to unmute myself on the PC. I did, but
Yeah, that means you're on the PC.
yeah. But how do if I mute? They couldn't hear, right, on the other end. Yeah, somebody asked, can you switch to the audio? What should I do? Mute.
Yeah, I saw that. Did he use?
I don't know. Like he did something. He called in there, but I have no idea how.
You should have used this one.
Yeah. Forehand.
It's oh shit, he probably didn't get it. Let's wait. Anyway, maybe you can still speak to this.
Okay, should I continue speaking? Okay, I'll try to get closer to the computer.
Right. Yeah, he'll come in.
Okay. Is it okay on your end? On WebEx? Okay, I'll try to be closer then. Until they come and okay. So basically, in addition to the issues that we looked at the large scale, we wanted to build the small scale infrastructures with FPGAs so that we can actually test these DRAM chips and really understand the scaling issues in a controllable manner. And we built this. This was on the bottom right was our first infrastructure. We built it for retention time testing, especially. And then later we did a lot of studies on errors and latency. I'm going to mention the retention time a little bit, but this is the infrastructure where we did a lot of RowHammer studies. And we later open sourced this infrastructure. It's all public. It's actually relatively easily programmable. We're going to release an even more easily programmable version soon, hopefully next month. And you can basically test any DDR3 chip with this one, and in the upcoming one, any DDR4 chip. And people in academia, as well as industry, use it. And they come up with interesting results in addition to our results, of course. So we'd be happy to help if people are interested in using this sort of infrastructure. And that's the paper that introduced infrastructure in more detail. So the reason we built this infrastructure was really to study scaling issues. And in my opinion, a huge scaling issue in DRAM is data retention. Basically, how long a cell can retain data. I'm going to briefly cover interesting things here, but I'm not going to go into a lot of detail. But basically, we wanted to get rid of refresh as much as possible because as DRAM scales to smaller technology nodes, retention times reduce. Okay, now my computer is a bit slowed down. Okay, and we don't want to refresh everything every 64 milliseconds. Today, actually, you're refreshing things at every 16 milliseconds at high temperatures, for example. and it's becoming worse, basically. Clearly, this is bad for energy, bad for performance, bad for quality of service. And we wanted to really understand the retention times of different cells and design memory controllers that are intelligent enough to understand the retention times and refresh cells as frequently as they need it to be refreshed. And this is really the retention time of profile of DRAM. This is what it looks like, basically. An overwhelming majority of cells, you don't need to refresh very frequently. So you can get rid of the refresh rates, 75% of the refreshes in most cases, as you can see over here. But of course, it's not that easy. You really need to understand what's going on in the device. This is very much dependent on location. This very much depends on the value of the cell and the cells around it because of the charge cell-to-cell coupling. And this also very much depends on quantum-like effects like variable retention time that you have, like randomly retention time varies. And you basically need some intelligent support from the memory control to really figure out what's going on in each cell and dynamically adapt to the retention time of the cell. Okay, that was the reason why we built infrastructure, and we wrote a lot of papers related to it. I'm not going to talk about them. I really still find this really fascinating. For example, we looked at how to handle the variable retention time, how to handle the data-dependent failures, how to exploit the memory content to overcome the data-dependent failures. And more recently, we've been looking at LPDDR. Cancel. I don't want to open that. LPDDR4 chips, and things are getting worse, basically. Retention times are getting worse. Variable retention time is getting worse. And as a result, manufacturers started including error correction codes. And we wanted to understand that also because the error correction codes were not exposed to the architecture memory controller. And we really wanted to understand that. And these are some papers where we actually reverse engineered some of the error correcting codes, as you can see. Okay, so there's more to talk about in retention time. It's fascinating, but I'm not going to talk about it. You can find a lot more information on our lectures, on our papers. I'm happy to talk about it separately if people are interested in this. But that was the real reason why we built our infrastructure. While we were doing studies with that infrastructure, we also had a flash memory infrastructure. I'm going to show a picture of that later. We did a lot of studies also, similar scaling studies, error characterization studies. And we looked at read disturbance errors, for example, in flash memory, which is a different mechanism. And based on the synergy between the infrastructures, we also wanted to look at different error mechanisms in DRAM. And that's essentially how RowHammer came about. Together with Intel, we studied these read disturbance errors. And essentially, we found out that one can predictably induce errors in most DRAM memory chips based on these studies. Sorry about that. No. Okay. So I've already said this, so I'm going to go into RowHammer a little bit more. So what is the problem, basically? It's essentially read disturbance. In a sense, there is nothing new here. The new thing is this is happening in DRAM. It's getting exposed to the real systems. When you activate one row, you apply high voltage to that row. When you want to this is called an activate in DRAM. And if you want to access some other row, you apply low voltage to this row. And then apply high voltage to some other row, to the word line, basically. You keep doing this repeatedly, activate, recharge, activate, precharge, activate, precharge, high voltage, low voltage, high voltage, low voltage. It turns out in cells that are physically adjacent, in the physically adjacent rows, if those cells are vulnerable, they get flipped. They basically lose charge because you do this repeatedly enough, you leak charge a little bit every time from a vulnerable cell. And if you do it enough times before the cell can get refreshed, you can actually cause this bit flip. And that's the idea of RowHammer, essentially. It's due to electrical interference that's happening between the different rows. Okay, basically, we showed that in more than 80% of the chips that were manufactured, that we tested, at the time, we could actually induce these errors. And our hammering mechanism was not the best, basically. It was single-sided RowHammer. Later, people invented, based on our results again, double-sided RowHammer, which is actually makes it much worse. So why is this happening? As I said very quickly, there are a lot of interesting device level papers that talk about it also, but I think the high level is lack of electrical isolation. Access to one cell affects the value in values in nearby cells due to electrical interference between the cells as well as the wires that are used to accessing the cells. And essentially it's coupling. And I like describing it like this. When we apply high voltage to a row, an adjacent row gets slightly activated as well. And vulnerable cells in that slightly activated row lose a little bit of charge. And if you do hammering enough times, activate, precharge, enough times, charge in such cells gets drained. Of course, you need to be able to do this enough times before the cells get refreshed. So clearly, one solution to this would be increasing the refresh rate. But we actually want to get rid of refreshes, right? So there are two scaling problems we have at hand. RowHammer, refresh. You can fix one by making the other one worse. And I think we should really be doing better, meaning fixing both at the same time. Yes.
Was there any study done on the 10 or 15% chips
Mm.
which did not flip?
So we did studies on that. We tried to flip them, but we couldn't, at
But-
least with a
but
single-sided.
did we understand
RowHammer.
why? That we could learn
Yeah.
a lot.
I'm going to show you a picture. Maybe these are older chips,
Ah,
meaning they're chips that are not where the cells are not close to each other. But in
oh,
some newer chips, we were also not able to induce. But I think later, if you actually do double-sided hammering, you could induce these errors.
And is there some like a geographical variation, like for example, the cells closer to the cell sap are they more or less? So the rows.
Yeah, that's a great question. So there's some spatial variation, but it's not as simple as you said. Basically, we couldn't find any. So there are some cells that happen to be much more vulnerable to RowHammer, but they're more randomly distributed if they're not that close to the sensor, for example.
And across the column, is there any variation?
Yeah, there's variation. I'm going to show that actually. So these are very good questions. Maybe we should jump to the back.
Essentially,
Yeah.
Are you essentially looking at an RF attack caused by the change of frequency in the adjacent line? So it's the radiation, it's the voltage switch that sends an electromagnetic pulse that's picked up by a wire in the adjacent row, and if the cell is at the right charge, you have the effect. Is that essentially what you're talking about?
I couldn't quite follow the first part, but
he's asking whether this is electromagnetic
oh,
rather than the capacitive.
no, it's really about the charge leakage in the end. It's really capacitive leakage. There are some underlying mechanisms that cause the charge leakage, yes, but it's really not electromagnetic. I can refer you to some device level papers that actually explain this effect a little bit more. Okay, so this device level problem actually has a huge implication on the upper levels of the transformation hierarchy, because DRAM is very special, right? It's directly exposed to the data structures, algorithms, programming languages, essentially operating system. Any bit flip over here affects the user almost immediately. And when we actually first showed this, we released code. This is a user level program, x86 code, 6 lines, as you can see. What it does is basically it selects addresses X and Y such that X and Y happen to be inside the same bank. And it basically hammers X and Y, avoiding cache hits in the CPU, avoiding row hits in the CPU, because you really need to activate them pre-charge. And basically this program does this at the high level. And later work improved this program, of course, much better than we did. And if the chip is vulnerable, you will get these bit flips. And the nice thing is if you select X and Y such that you sandwich one row, I should not go far away, one row in between X and Y, then you get even more bit flips. Like we mentioned that in our paper, but we didn't analyze it much. Later work actually built on it, and they basically showed you can get even more bit flips. Okay, so this is our work from 2014, Intel, AMD, we tested them, but there's nothing special about Intel and AMD. As long as you have memory controllers that can do this activate and pre-charge enough times within a refresh interval, and all memory controllers are actually capable of doing that today, because the issue is actually getting worse also, you can induce these errors. And this is a real reliability and security issue. Was there a question? I heard something. Okay. It's a reliability issue, clearly, but it's also a security issue because it really breaks memory isolation. And this is what we said in our original paper. Memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on other addresses. And I still believe this is really important, because everything that we assume is built on top of this, right, in terms of security, safety, reliability. And we said that actually someone can hijack your computer by this. We didn't develop that attack fully, but later Google Project Zero folks showed the first attack building on RowHammer. They basically had this nice black hat presentation and blog post. If you're really interested, I'd encourage you to read it. I have links to it over here. And I copied and pasted some of the sentences from their work. They basically replicated the problem. They found out that it exists, and they built 2 working privilege escalation exploits. They're both interesting, but one is a lot more interesting. One takes over the Google native client, essentially a virtual machine, but the other one takes over the x86-64 Linux kernel. And the high-level idea is you have a user-level process, and this user-level process hammers its page tables, and essentially it's able to flip write bits in its page table such that it can gain write access to its own page tables. And if you gain write access to your own page table as a user level process, then all bets are off. Essentially, you can do anything you want to the system because you know the structure of the page tables and you know where operating system stores critical data. You can get access to everything basically this way. Of course, it's easier said than done. They have a beautiful security engineering over here, like page table spraying. It's actually very beautiful. Later, I'm going to mention another paper toward the very, very end, actually. I'm going to mention another paper that actually did something like this in 2003. But this became a lot more interesting because you could do this through RowHammer this way, right? In 2003, we're going to take a look at it basically. Maybe I should not spoil it at this point. Okay, sorry. Any questions? Let me do this. I want to make sure people can still see things. Is that okay? Okay, you can probably let me know if that's not the case. Okay, so basically, this is known as the RowHammer vulnerability now, and they're really interesting. A lot of hackers got interested in this, actually. This is a very famous hacker who said on Twitter, it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations opened the door you were after. And I think this is a very, let's say, nice explanation, right? Okay, I'm not going to go into a lot of the security research that built on it, but I'll point to some interesting ones. These folks from TU Graz show that they can gain unrestricted access to systems of website visitors using these RowHammer bit flips through JavaScript. These folks, showed that you could actually do this on an Android phone, and you could download their app at the time, at least, and this user level program could take over your phone directly. It's very interesting, actually. This is a very nice paper to read if you really want to understand how a RowHammer attack gets built, let's say, at the software level. And then, okay, sorry, something is going really fast in my computer. So these folks show that you could do these attacks much faster via GPU on a cell phone because GPUs can access memory much faster. These folks show that you could do this over a data center through the RDMA, remote direct memory access interface on a remote machine, essentially. These folks showed essentially the same thing. These folks show that, okay, even if you are not able to take over a system, you could leak private data. This is a recent work, as you can see. You could break confidentiality, basically, even if you cannot take over the system. And more recently, there's actually a lot of interesting work that's still happening on neural networks. And people have shown that in neural network inference, if you somehow induce these RowHammer bit flips, you can turn an otherwise reasonably accurate neural network, in this particular case, for example, 90% accurate, to a network that's essentially useless. Its accuracy is 10%. And this is not the latest paper. There's, I think, another paper coming up. I saw that recently in a security conference this year that talks about essentially something similar. So I think this is very interesting because you could build a very nice neural network engine, accelerator, or whatever, and it may not be very useful. It may be actually very safety critical. And if a reliability or security problem like this happens, your safety may be at stake, right? Okay, so there are other papers that I'm not going to talk about. This may be one solution to the problem, but I would not argue, suggest this.
In the neural network case,
Sure, this one.
If it's a weight memory, that's read only, right? Or how, people are deliberately attacking?
Yeah, they're deliberate. In this particular case, they're deliberately attacking. Not. I don't think they have any paper that I have seen has shown that this happens like in a benign neural network inference application, but deliberately you can attack an application that way.
What's the privilege mode you need for doing the attacks? I mean, you can do some escalation, I guess, once you hammer it, but just to do the attacks, you need like.
Yeah, you don't need any privilege mode, basically. If there's no detection mechanism, basically you could keep hammering, activate pre-charge. And you will see later results, actually. In our original paper, you needed to do 139,000 activate pre-charges to induce these bit flips. Today, the number is around thousands.
Okay.
So detection is becoming also much harder, right, at the software level, for example. And hardware overheads are growing because of the small number of hammering that you need to do to induce the bit flips.
But in the neural network application, again, if you make it a read-only memory, if you use only read-only memory, then this problem goes.
Not necessarily. If someone hammers the read-only memory, they're still reading, right? They're not writing. They're activating differently. Exactly, because activation is still reading.
But you can deliberately keep reading, I guess.
You can deliberately keep reading, and then you corrupt some bits because of that. And as a result, your accuracy goes down. That's what they showed. They're not taking over the system, so they don't require write access, basically. Yeah. That's the interesting part, I think. So the threat model, basically the attack of taking over the system is very strong, but these neural networks are much less strong, let's say. You just need to induce these bit flips at the, let's say, right weights, or enough of these bit flips in your weight memory so that the accuracy tanks, let's say. And there's another paper. I'll try to find it. I didn't have time to actually put it in the slides. There are more papers coming up in the neural network domain for defenses as well. Okay. Okay, so there's a lot more to talk about. This was a survey paper that we were invited to write in the special issue of TCAD. If you're really interested in, like at that time, the state of the RowHammer, this covers devices, this covers circuits, this covers architecture, this covers security, and this covers more general. And there's a lot of research that has gone on, and we're going to update this paper at some point. What I'm not going to talk about, what this paper doesn't talk about is stuff that's done after, of course, 2019, which I'm going to talk about soon. Yeah. Sure.
Do you need more reads?
That's a great question. So it's activates. In the end, you just need activates to induce RowHammer. So read or write doesn't matter, basically. Exactly, no difference at all. We did test that in our original RowHammer paper. It doesn't matter, basically. Yeah, there are a lot of interesting things, but I'm going to tell you some other things that we've tested recently that make a big difference. Not reads, writes, but how long you wait before you do the next activate makes a difference, actually, because there's some circuit level charge buildup that happens. And if you wait a little bit longer before you do the next activation, this actually makes the hammering effect much worse. Yeah, we have some real results. Yeah, it's very interesting. So basically doing it extremely frequently is not the right approach to actually, if you want to induce the bit flips, more bit flips. Because you need some charge buildup. Again, we don't fully understand the device level mechanisms because I'm not expert in that. Exactly. Exactly. Yeah, there's some basically time window over there.
Multiple rows at the same time, like
Yes.
Multiple combinations of.
Yes.
Okay.
Yes, we're going to talk about that. Yeah. So if in the absence of a defense mechanism, hammering two rows and with a victim row in between is the best. That leads to the highest bit flip rate and also highest the fastest bit flip, the smaller number of hammers to get to the first bit flip. But if there's a RowHammer protection mechanism present, then you need to hammer more rows to bypass that protection mechanism, as we will see. These are great questions. If there are questions on Zoom or WebEx, I'm used to Zoom. WebEx, I'm happy to answer also. But before we go into the later works, let's try to understand it quickly a little bit, because these are going to be, I think, very fundamental for solutions that are being developed in the future. So we did a lot of studies with our infrastructure starting from 2012. And we tested at that time 129 total modules. Sorry, I skipped one important slide because I think my computer made me skip it. Now I realize it. This is the slide that answers Pradeep's question, basically, at least partially. But basically, somehow this went very fast. This is really a technology scaling problem, as you can see, right? The chips that we tested before 2010 were not vulnerable. Everything that we tested that was manufactured between 2012 and 2013 were vulnerable. And there's some anomalies over here, as you can see, but I think with double-sided RowHammer, they're also vulnerable, actually. So basically, in chips that were manufactured before 2010, this problem, you needed to have a lot of hammers, and you couldn't do enough hammering before the cells get refreshed. In 2010, cells became closer to each other, the noises increased, and electrical interference increased. As a result, you could fit enough hammers before the cells get refreshed. And this scaling problem is getting worse today. The number of hammers that you need to do before the cells get refreshed to induce bit flips is actually reducing significantly. So this is really a technology scaling problem. And this is the first picture. I'm going to show you even more evidence to this technology scaling problem later on. Sorry, this is the downside of computer going too fast. But that is the first important analysis, in my opinion. So there are other analyses. Clearly, I've given you some of them. Errors are because of the charge loss, it happens. Let's talk about the adjacency, because this is very interesting from a solution perspective. So from a memory controller perspective, what is the relationship between the addresses, row addresses of the aggressor and the victim rows? Are they adjacent from the memory controller perspective again? And most of them are adjacent, as you can see. The distance is plus minus 1. Row address difference, of course. But some of them happen to be non-adjacent. The question is, does this mean that they're physically non-adjacent? And the answer to this we have is not necessarily, because internally the DRAM chips do remapping of rows. And the reason is fault tolerance purposes mainly, actually, reliability purposes. Because you can, for example, map a row to another row if you find a defect in one row. And as a result, you hammer, memory controller sees one address, it hammers it, and some far away row from the memory controller's logical address space viewpoint may get bit flips. Now, this is important because this means that memory controller, whenever it's fixing the problem, it cannot assume that the bit flips are happening in adjacent rows. Most of the time it will be correct, but some of the time it will not be correct. So I think it's good to think about this. Okay, access interval, clearly this determines, at the time we tested this, this determines how many errors you can cause. Here we basically increase the access interval across the board to the aggressor, and we see fewer bit flips as access interval increases, as you can see. I'm going to show you something else later on. Here we do activate precharge. We don't keep the aggressor active, basically. We do activate precharge and distance those activate precharges more as you go from left to right over here. And less frequent access clearly lead to fewer errors. So one way of solving the problem is reducing the frequency of accesses, but this is not good for performance, of course, right? Okay, the other is the refresh rate. Clearly, as you increase the refreshes, you get fewer errors. So as you go to the left on this graph, and these are real data, as you can see, these are the worst chips from 3 major manufacturers over here. As you go from right to left, you do more frequent refreshes. And if you really wanted to get rid of every single error that we observed in our chips, you need to increase the refresh rate by 7x. So clearly, this is not good for performance and energy. But this is going to be the solution that's implemented in industry, because that's the level of programmability that we have in our memory controllers today. Right? So data pattern is interesting. If you look at the data pattern on the right, you get an order of magnitude more errors because the coupling is much worse because of the voltage coupling that you have across different capacitors right over here. Okay, so these are very interesting things. There are a couple more very quickly. I'll go over them. The error mechanisms between refresh and retention time and RowHammer are very different, basically. Even though they're both based on leakage in the end, the leakage paths are very different in this particular case. As a result, retention weak cells have almost no overlap between RowHammer vulnerable cells. This is very interesting, I think. Errors are repeatable, meaning if you can induce a bit flip in one cell, you're going to be able to induce it again and again and again. So you can actually profile memory and figure out which bits are vulnerable, and you can attack memory based on that vulnerability later on. This makes it an even worse security problem, let's say. You get as many as 4 errors per cache line. We're going to revisit this with real data again later on. This is also real data, but basically simple ECC mechanism cannot prevent all errors. And then finally, this is double-sided hammering. This is what led to double-sided hammering. We showed that cells are affected by 2 aggressors on either side. As a result, you can get more hammers if you sandwich one row, basically. There's a lot more in our original paper. I'm happy to talk about it, but let's move on to, let's say, newer things. But before that, I'll talk about solutions, initial solution thoughts that we had. So basically, we're going to move on to some newer things after we talk about some solutions. But RowHammer is getting much worse because technology scaling is much worse. This is a recent paper. And more recently, we've been looking at new RowHammer dimensions also. I'm going to talk about that. It's also fascinating. And we have one paper coming up at DSN where we study the word line voltage effects on RowHammer. I'm going to talk about that briefly also. But before we jump into more analysis, let's talk about solutions. I think this is important clearly because if you have a problem like this, you want to solve it immediately in the field because all of the chips that are out there are vulnerable. Clearly, there are limited possibilities here today because we don't have memory controllers that are like extremely capable. But longer term solutions can be much stronger, let's say. We can have a wider range of protection mechanisms in the memory controller, in the DRAM chip, and maybe at the system level also. So in our paper, we proposed 7 solutions in total. And I'm going to talk about Para, which is the best solution at the time, let's say. But today, I think it doesn't scale very well, basically, according to our recent studies. I'm going to show you that also. So we really need better solutions going into the future. So at the time when we first thought about this or studied this, these were some of the solutions that we envisioned, let's say. Clearly making better DRAM chips with better materials. It'd be great, but cost is a big problem over here. Refreshing frequently across the board. We said that this is clearly practical and it should be done perhaps, but unfortunately, this is not a good long-term solution. ECC, we argued that it's not a good solution because the ECC is very good at random bit flips, right? But this is, yeah, if you really want to protect against this, you want something more intelligent, let's say, than just broad ECC. And finally, access counters, we were actually a bit pessimistic on this, but I'm going to, let's say, pull back on that a little bit because access counters mean that can you somehow identify which rows are being accessed a lot and do something about it, basically. And I think people have developed a lot of interesting mechanisms recently to show that this is maybe a good direction going into the future, maybe combined with some other things, as we will see. Okay, but in the end, I think everything comes with some overhead. The key question is, like, can we find a good trade-off to solve this problem so that it doesn't become a security, safety, reliability problem? Okay. Okay, so what was the solution that was employed by most of industry? I think all of industry, but this is Apple's security patch. Basically, they say to solve RowHammer, they increase the memory refresh rates. They don't say by how much. I assume it's 2x, but yeah, but they were nice enough at least to say this, and they were nice enough also to attribute to our paper at the end. So our solution was basically, it was very simple. Yeah.
It's OS X. Is it also done for iOS?
So
is it across basically across all platforms?
I believe it's across all platforms, but again, I don't, I cannot guarantee that. I'm not working at Apple, so my belief is yes, it's across all platforms.
Okay.
I just assumed this patch basically carried over, let's say, across all platforms. But again, I cannot.
Both LPDDR and for
Exactly, yeah, especially LPDDR, yeah, going into the future, because it's getting much worse as we will see. Yeah. Okay. So our solution was very simple. It was probabilistic, basically. The idea was whenever the memory controller closes a row, it activates one or both of its neighbors with very low probability. And the probability is, you can see 5 out of 1,000 times. It could be. And we studied different probabilities, of course. And if you're paranoid, you can change that probability, of course, right? With that probability and with the hammer counts that we saw at the time, we said you could get actually a very good reliability guarantee, much better than hard disks at the time. And again, adjusting the value of P is nice because it gives you a protection against errors at the cost of more performance overhead, right? So performance overhead comes from refreshing more, clearly, but we're not doing, we're refreshing in a very targeted manner, probabilistically closing the rows. Whenever we close a row, we do it. So if you don't increase the refresh rate across the board in this particular case. Now, we showed that at the RowHammer vulnerabilities at the time, this is low power, low performance overhead, it's stateless, low cost, low complexity. You need to have a random number generator, but we're actually working on random number generators in DRAM also that I'm not going to talk about. So I don't think you really need the random number generator for this particular solution, but let's not go into a lot of details in this particular solution because there's a lot more to talk about. So at the time, we argued that this is effective and low overhead. I believe this is actually still a good spark of an idea. But if you do this at the RowHammer counts that we're seeing today, it's actually a very high overhead. Its overhead increases, as we will see. Cost doesn't increase. Cost and complexity are nice, but the performance overhead due to the extra refreshes is higher today. Okay, the good news is I think you could do this in the DRAM chip as well as the memory controller. So in existing DRAM chips, some of the DRAM chips actually employ some of these ideas, variants of these ideas, because so the idea is to DDR protocol is not very flexible. As a result, you need to have some slacking or refresh parameters. And what existing DRAM chips do is because of the slack that's present in refresh latency, they can induce some RowHammer protecting refreshes internally. That's the idea. And we're going to talk about that later on. If you implement in the memory controller, we argue that you need better coordination between the memory controller and DRAM so that memory controller knows exactly which rows are physically adjacent. And I think this is still a good direction, frankly. We need better cooperation across our components. Now, the good news is that Intel actually implemented a version of this, a variant of this. It's not exactly how we envisioned it, but they have this BIOS. As you can see in the BIOS, you can pick your RowHammer solution, either hardware RowHammer protection or 2x refresh. And hardware RowHammer protection is essentially a version of Para where you can pick the probability, let's say. I mean, internally, it's slightly different as far as I understand, but it's the same basic idea. With some probability, you can pick. Now, unfortunately, I'm going to give you the story later. Later, DRAM manufacturers said, we solved the problem. Our chips are RowHammer free. So this, let's say, nice direction in the memory control, intelligent memory controllers were kind of dropped, let's say. But we're going to talk about that story soon. Okay, so if you're really interested in other solutions that we propose, there's a lot more in this paper and also in the longer survey paper. But I think my takeaway from this is we really want intelligent controllers if you want safety, security, reliability, and scaling. And these all go together. I mean, I'm talking performance is a given, I think, over here, performance energy.
By intelligent controllers, you mean something which can detect that it is being attacked.
Either detect it or do it probabilistically, like we propose, depending on the level of intelligence, right? Yes, I think so. It's something that can basically solve the RowHammer problem. And this intelligent controllers can sit on the memory controller side or the DRAM side. I think maybe both, maybe also at the system level a little bit. I think we need to really explore the space. I'm going to give you some more examples of this soon. So, and we're used to building intelligent controllers, actually. This is NAND flash. I promised that I would show you the infrastructure that we had built to study a lot of characteristics of NAND flash. And NAND flash actually has an intelligent controller. NAND flash is a memory that doesn't work off the bat, right? It has a lot of reliability issues, and the controller makes it work. I think the mindset in DRAM has been very different. DRAM is very strong memory. It's been assumed to be working all the time, and the controller just controls it, but not make it work. I think maybe we need to change our mindset a little bit in terms of how we design controllers for DRAM going into the future. And if you're really interested in flash controllers, this is a summary of the work that we have done and that others have done in the field on error characterization, mitigation, and recovery. Okay, so those original works, we have a lot of lectures, you can find them. And as I mentioned, we have written some papers that summarize the problem and also cover a lot of work in the field. But now let me jump into what has happened in more recently. I think this has been fascinating because people kind of thought, okay, DRAM manufacturers solved the problem, so let's just move on, right? But we're going to see that that's not the case. So first of all, we revisited RowHammer from a device level perspective. We wanted to ask the question, okay, we did these studies 8 years ago, 7 years ago. What has happened since then? So this paper did study a lot of chips, many more chips than we studied originally. And these are the key takeaways basically in one slide. We studied more than 1,500 DRAM chips from 3 different DRAM standards and multiple different generations. And the takeaway is newer DRAM chips are much more vulnerable. You get more bit flips, and bit flips are happening earlier with fewer activation counts. As you can see, that one number is over there. There are new chips whose weakest cells fail only after 4,800 hammers. This is double-sided, granted, so it's really 9,600 hammers, but less than 10,000 is still pretty disturbing. And chips of newer DRAM technology nodes exhibit bit flips in more rows. So RowHammer effect is actually kind of not just the adjacent row, but there's a weaker effect on the second adjacent row and third adjacent row, etc., and farther away, basically. And the last point that's also very important is we study the scaling of existing mitigation mechanisms that were proposed in literature as well as kind of implemented in industry. And we found out that they're not effective at future technology nodes. So for example, if you go to 1,000 hammers to cause a bit flip, para is not as good. It still works, it's scalable, but its performance overhead becomes, let's say, 20%, 15%. And the paper has a lot more detail on that. Some mechanisms don't even scale because they're not really designed that way. So let me go over quickly on some of the results. And feel free to please ask questions. I don't know if people are still hearing on WebEx. Okay, I hope they're not just hanging out and not hearing, because that sometimes happens in meetings. But these are we actually built a lot of infrastructure for this purpose. You can see we tested DDR3, DDR4, LPDDR4 chips. And I'm not going to cover this busy slide. This is basically all of the chips that we've tested and their different generations, different manufacturers, as you can see. So we wanted to really do a scaling study. And let me give you one result from that scaling study. This is 3 different manufacturers, ABC. If you focus on the blue curve and the yellow curve, blue curve is old generation DDR4, yellow curve is new generation DDR4. You can see that the curve shifts. This curve basically, on the x-axis, you see the hammer count to induce the first bit flip, and the RowHammer bit flip rate, meaning error rate, let's say, if you do that hammer count. You can see that the curve is shifting from to the left and up higher, which means that you're getting bit flips earlier with smaller hammer counts, as well as you're getting more bit flips. And this is, I think, a nice scaling result across many DRAM chips, across manufacturers. Unfortunately, we didn't have the infrastructure to. The difficult thing with the DRAM studies is every single DRAM generation requires a different infrastructure, right? Because of phi is very different, and we don't have the luxury in academia. Even companies don't have the, I think, luxury to actually do all 10 different phis, let's say. Yeah, I would love to. So if you have the infrastructure and want to collaborate, I'm happy to look into it. So those guys did it on a real system. So on a real system, I guess, yes, you could do these studies, yes, but then you're really not understanding exactly what's going on, right? We wanted to do this device level scaling study where we build the memory controller ourselves also. Yes, that's a good point. But I think though, in that particular case, it was also a DDR3. It was a cell phone, basically. Oh, it is not. Yeah, it was a real cell phone. It was not a very high-end thing. Yeah. Okay, so I think I've given you the key result. So this is another result. This is also interesting, I think. When do you get the first RowHammer bit flips? Oh, sorry. You can see that based on the arrows over here, you can see that newer DRAM chips from each manufacturer are more vulnerable to RowHammer, meaning you get the first flip at a lower hammer count. On the y-axis is the hammer count needed for the first bit flip. We call it HC first, hammer count, first bit flip, let's say.
And the main reason is density.
Exactly. Main reason is density, basically. Cells are closer to each other, smaller, and this noise is becoming much worse. Okay, so there are a bunch of numbers you can find in the paper clearly. And that's the paper. It has a lot more data than what I just described over here, but we don't have a lot of time. And if you don't want to read the paper, there's a lecture also. We have all our lectures open, so feel free to take a look. So, okay, as I said, DRAM manufacturers said they actually solved the problem. They basically said our chips are RowHammer free. They said this publicly. At least 2 manufacturers said this publicly. They said trust us. Unfortunately, they didn't say how they solved the problem. So we kind of took this as a challenge. So we wanted to really see what has been done, and is the problem really solved? Should we not work on RowHammer, let's say? And the answer is basically the problem is not solved. Industry adopted solutions are not fully secure, let's say. I put do not work over there, but it's true. I think if you claim that something is solved, it better be solved, right? Especially something that others can test. This is, we call this trespass, TRR pass. So TRR is the general idea, target row refresh. This is in the DRAM standard. And the idea, it's really an umbrella of solutions that say target rows are refreshed. And it's not described in any meaningful way, let's say. Every manufacturer implements in a different way. So you don't know how it works. We tried to figure out how it works, basically, and bypass it. This is the first work to show that TRR protected DRAM chips are vulnerable to RowHammer in the field. Basically, mitigations advertised as secure are not secure. And the way you bypass these solutions is to really reverse engineer just a little bit so that you can bypass the protection mechanism internal. So we introduced what is called the many-sided RowHammer attack. And the idea is you hammer not just 2 rows, but more rows so that you can overflow the underlying protection tables, let's say. And our hypothesis was that there are some protection tables inside the DRAM chips that count accesses to different rows. And if we can somehow overflow them, basically we can fool them and we can still induce bit flips. And we were right in many cases, as you will see. Okay, because of solutions are not really security proof, let's say. Okay, I already said this basically. We reverse engineered, and we also provide an automatic tool that can effectively create many-sided RowHammer attacks. So you can download this tool and try it for yourself. Now, later work from Kaveh Azavi's group, whom we collaborate with, actually provide a much better tool. It's called Blacksmith and Smash. I'm going to mention those papers soon. You might want to test those tools instead of this older tool, but they're based on this tool, basically. Okay, so these are some hammering patterns. So you can see this is a 3-sided RowHammer. It's double-sided, we call it. This is a 4-sided. Basically, you don't just have 2 rows that you hammer, you have more so that you can overflow the tables. And these are some real results from real chips. Now, there's some noise, of course, but for example, for this particular module, you need to have 5-sided RowHammer to induce bit flips. 6-sided doesn't work because there's some internal mechanism that happens to catch 6-sided in this particular case. We didn't fully understand what's going on in this work, but later I'm going to show you a Micro 2021 work where we almost fully understood what's happening internally. Here, our goal was to actually understand just enough so that we show that the mitigations are not secure. Okay.
As you increase the degree of hammering, though, isn't there like performance degradations that show up?
In a system level, right? So yes, exactly. I mean, that was not our goal over here, but yes, certainly at the system level, your performance decreases. So, and that could be one way of like detecting something is going on. Yes, yes, I think so. I think so. The question is, can you do it quickly enough? Let's say, well, before you get before someone actually induced a bit flip. I think that's the difficulty with, let's say, software level solutions that try to look at performance implications, because things like that have been proposed actually as early as ASPLOS 2016. Anvil was a mechanism that proposed that. Always the issue is, can you really catch it early enough? Do you have enough performance counter space, let's say, to be able to do that? But I think that's a good direction to think about. Yeah. Okay, there's a lot more interesting things over here, but to discuss. For example, as you go to higher number of aggressor rows, it doesn't always mean you get more bit flips because you're hammering less some of the rows. Clear there's a trade-off over here. And the trade-off is noisy because we don't understand what's going on in the underlying mechanism perfectly. But the key is really we can induce these bit flips, even though it was said that you cannot induce them, right? So you can see we were not able to induce them in all of the chips that we tested. Some of them you need 19-sided hammers to get the best. So even 19 rows, you can see that. It's very interesting, I think. Yeah, and we actually showed that you could induce bit flips in real phones also. So we collaborated with security researchers who were experts at actually doing this. So they did these attacks where they showed that you could actually take over. These are three major type of RowHammer attacks over here, and you can see that in these cell phones that are equipped with these modules that are supposed to be protected against RowHammer, you could still take over the system. Okay, so that's the takeaway basically from this work. I think these results were just scratching the surface. The tool is not exhaustive. There's a lot more we could have done actually to make it exhaustive, but there's always a return on investment issue at some point, right, in research also. But there's a lot more. Yeah, I'm going to get back to this actually. Yeah, we have studied this recently. We're still studying it actually. I'm happy to talk about it soon. That's one of the more recent works. In this one, we're really looking at still can we bypass things, not understanding things. Okay, but basically the takeaway with trespass was RowHammer is still an open problem, and security by obscurity is likely not a good solution. It's probably better to have a more open mindset and try to say, okay, this is our solution. Let's try to break it so that we can have a good solution overall in the system. Okay, there's detailed lectures on trespass also. Later, we asked the question, can we somehow guarantee that a chip is RowHammer free? I said later, but it's really concurrently. We're doing these works concurrently. I'm not going to talk about this. I think this is a really, really important question also, but really our answer is really not positive to this. I don't think we know of a way to guarantee this. On a real system, as well as even if you have the chips and you have the testing infrastructure and you know a lot about the chips, it's very difficult because there are a lot of dimensions. This is a work that we've done with Microsoft and folks at MIT, as you can see. And there's a lot of interesting data here. And it basically shows that on a real system, the hammering patterns varies very widely in terms of which instructions you use, for example. So it's very difficult to guarantee. But let me jump into the other work that builds on trespass. After trespass, we said, can we really understand the existing solutions much better, basically? And we wanted to uncover the existing solutions almost completely. And we found that, well, maybe this is a provocative title over there, so that maybe to get the industry to do. I mean, yeah, these are for manufacturers, not for IBM at this point. Actually, our argument is really memory controller vendors and DRAM manufacturers should work together to come up with a much better solution. I know there are political and business issues over here, but I think initial solutions were in the right direction. Let's say memory controllers were doing stuff, but pulling everything into the DRAM with a not so great DRAM interface didn't really help, let's say, in my opinion. We can talk more about this, of course. But basically, what we did in this work is we're going to release actually our infrastructure very soon. We're working on it because we want to release our DDR4 infrastructure. We cannot release this infrastructure before we release our DDR4 infrastructure. But basically, we wanted to easily study the security properties of TRR and validate its security guarantees. And this introduced a new methodology that leverages our expertise in data retention failures to uncover the inner workings of TRR and to study its security. And the idea is actually very interesting. You use the data retention failures as a side channel to figure out whether internally the DRAM chip refreshed the role. Now, the DRAM chip may refresh a row for two reasons. One is periodic refresh induced by the memory controller. The other is because of RowHammer protection. Right? Clearly, RowHammer protection refreshes are not visible. Internal refreshes are also not visible, but at least you basically memory controller doesn't know which rows are refreshed, but it induces refresh commands. So basically, we have a way of figuring out what refreshes are caused by RowHammer protection and what refreshes are caused by regular refreshes here. So we can reverse engineer what's going on underneath. If you really want to know more about it, there's details in the paper, because this requires retention time profiling of DRAM rows. So you figure out some DRAM rows that are not supposed to be refreshed. Basically, they're going to lose their value unless they're refreshed, and you're going to hammer them. And if you see a refresh to them, you know that it's going to be refreshed. It's being refreshed because of TRR mechanisms, basically. And if you do this, now you can understand what's going on underneath much more better. We can craft new RowHammer access patterns, and we did actually craft new RowHammer access patterns. They're described in the paper. I'm not going to go into this. And all 45 modules we tested were vulnerable to RowHammer. So this is a significant improvement compared to trespass. And more than 99.9% of rows in a DRAM bank experience at least one RowHammer bit flip. And we actually were able to induce up to 7 RowHammer bit flips in an 8-byte data word, making ECC ineffective, completely ineffective, actually. So basically, we conclude that TRR doesn't provide any security against RowHammer, but hopefully based on this understanding, we can develop better mechanisms. So I've already described the basic idea. I'm not going to go over the details since we don't have a lot of time in this talk. I'm happy to talk about details. It's actually based on our FPGA-based infrastructure again. And that's what enables us to really do this. You cannot do this on a real system. You really need to control the access patterns that you have to DRAM and figure out the retention times and then identify which rows are refreshed by whom. So you need to craft the access patterns also. And again, this is our infrastructure that enabled this. Okay, I've already said a lot of this. Let's take a look at this paper. This is interesting, I think, this table, sorry. You can see that we have 45 modules and different manufacturers actually employ different mechanisms. So we reverse engineered almost all of it, given some amount of time. You can see some of them are using counters to detect which rows are being hammered. Their capacity is 16, meaning to overcome this, you need to hammer more than 16 rows or do something. Some of them have per bank counters. And the ratio between target row refresh and regular refresh is 1/9 over here. And you can see that some chips are refreshing neighbors, 4 neighbors, as opposed to just 2 adjacent neighbors, because they are aware that the problem is actually more widespread. Some other manufacturer, you can see it's more sampling based, like para, typo based. As a result, its aggressor capacity is much lower. It's not per bank, but its refresh ratio is much lower, let's say. Yeah, and some of them, it's a mix. And we didn't have enough time to really uncover exactly what is the aggressor capacity. Yeah, it's very interesting, basically. The key is you can almost completely reverse engineer. And we believe that actually, if we dedicate enough time, you can reverse engineer essentially almost everything. But at some point, it doesn't become the right trade-off for a PhD student, right, to do this. And the key takeaway is, if you do this, you can basically induce bit flips in all of the chips that we tested. Okay, and ECC doesn't help, as we discussed. Okay, there's a lot more in the paper that I don't have time to cover. I'm happy to cover after the talk. Okay, if there are no questions, let's talk about more analysis now. This was real chips. Can we do something about them? We also wanted to do more analysis, and this is also published in Micro 2021, this October. And we really wanted to understand 3 major characteristics: temperature. How does temperature affect RowHammer? How does aggressor row active time affect RowHammer? And how does spatial variation affects RowHammer? And our goal was to actually both improve attacks as well as defenses, because if you really understand all of this, from an attacker's hat, you can improve your attacks. From a defender's hat, you can improve your defenses. Again, we extended our infrastructure to do a lot better temperature control. We can keep the temperature stable at 0.5 degrees Celsius level. And we tested a fewer number of chips in this particular case, because these are extremely long tests, actually. Yeah, you can see. And we also added 1 more manufacturer. And the trends are actually very similar. So we named the manufacturers also. I mean, it was kind of.
In this case, you are allowed to name?
Yeah, I mean.
They're allowed.
I mean, we've always been, this is all public information in the end. And I don't get actually funding from any of those companies. So maybe if they fund me, I'll think about maybe not. But I think the key is here, it doesn't matter. The manufacturer really doesn't matter. The trends are always the same. It's all scaling issues. And even Nanya, the last manufacturer, which is a much smaller portion of the market, they're also vulnerable to RowHammer, and their characteristics are similar, basically. Okay, so there's a lot of conclusions in this paper. I'll mention a few and give you results on a very small portion. Some of them are actually quite surprising to us. For example, we found out that different cells are vulnerable to RowHammer at different temperature ranges. So some cells are vulnerable between 50 to 70 degrees. Some cells are vulnerable at 80 to 90 degrees. And we call this exact same chip. Yeah, this is a vulnerability range. We call this. Different cells are vulnerable to different. Yeah, we don't completely understand the device level reasons, and there's some work that we cite that talks about this, but again, it's very hard for us to completely reason about this, let's say, but this is what we found on real chips across many times of testing. The second one is if the aggressor row is active for a longer time, as I said, if the row is activated, but you're not pre-charging it and you keep it active for some amount of time, you get more bit flips in that row, and you reduce the HC first, which is the hammer count. And again, physical variation exists. I'm going to show you some results on those. Okay, let's take a look at the first one, for example. So this is activating aggressor row as frequently as possible. Activate pre-charge without keeping it active for some time. And the second part over here is keeping the aggressor row active for a longer time. You get 36% reduction in the hammer count that you need to do to induce the first bit flip. And this is important clearly for defenses. So if a defense, usually defenses are configured based on this HC first value. What is the RowHammer threshold? Like, are you going to get the first bit flip at 10,000? And a defense may be configured with some guard band, of course, right? Now, if this 36% is greater than the guard band, the defense may not work, right? That's the idea over here. So attacks and defenses need to improve based on this information, let's say. So spatial variation is also interesting. Basically, we saw significant spatial variation, but within the same subarray or across subarrays in the same DRAM module, we see actually similar things. So you can perhaps make your profiling easier. Let me give you some example of spatial variation. This is from one manufacturer over here. These are different modules. Different colors are different modules. Y-axis is the minimum activation count to observe the first bit flip. And the distribution is really different rows. So this is 99% of the rows. So you can see that some rows are extremely vulnerable. Some rows are not that vulnerable over here, right? The activation count is very high. And this is similar across different modules, except the exact values change. And so the takeaway is there is a spatial variation across DRAM rows.
But you don't know, like, it's not like the vulnerable rows are just.
So we tried to find that there's some information in the paper. I'd refer you to the paper, but we didn't find extremely consistent. Like, we cannot say basically rows that are closer to sense amplifiers are more vulnerable, for example. We wanted that also, actually. We really wanted that sort of, let's say, design-induced type of variation, but we couldn't. I think it's a lot of it is random process variation. We're still trying to find something, but we couldn't yet. Okay, you can see that different manufacturers are also similarly vulnerable. Maybe exact values change, but the curves are all very similar, as you can see. Okay, so columns, as you asked, Karthik, columns are also, there are some columns that are very vulnerable. You can see some examples over here. And again, you can see there's some randomness over here, right? And this is just some examples. There's a lot more data in the paper. Summarizing data is sometimes difficult. Okay, so somehow if you figure out this information, you can actually improve defenses. So this is actually a representative picture over here. 10%, 90% of the rows are not that vulnerable to RowHammer, but 10% of the rows are very vulnerable. So you can see the HC first is half of the other 90%. So if you actually figure this out, unfortunately, you had to do it on a chip basis, module basis, let's say. So you need to do testing, online testing, whatever testing. You can actually make your defenses much better. So these are some more state-of-the-art defenses. I'm going to talk about block hammer. Graphene works in a similar way, trying to detect aggressor rows, basically. You can get rid of a lot of the area overhead of these defenses if you really adapt to the module. But of course, this is high overhead to do the profiling. And I mentioned the temperature also. You can leverage, for example, potentially you can disable some rows if they're operating at their vulnerable to temperature range. I don't believe these are very practical, frankly, but I mean, from academic perspective, it's good to at least put out the numbers and maybe someone can use it, right? Who knows? But I don't believe, especially the second temperature one is not that practical. The first one, if we can find some, let's say, a non-random behavior in the spatial variation, I think it could be more practical. There's more analysis in the paper, and I'd recommend you take a look at it, or we can talk about it. So there's more coming up. As we discussed, we're looking at the word line voltage. These are some old results, but the takeaways are similar. Essentially, voltage swing on a DRAM's word line causes RowHammer in the end, because the higher the voltage swing, the more interference you will cause. That's the idea. And this is, well, theory, circuit theory at least. And there's some works actually that showed this, but there's no real work that like proved this. So our goal was to actually experimentally demonstrate this, or at least validate this hypothesis. And these are some old results. We have actually much better results right now. We basically validated RowHammer vulnerability can be reduced via voltage scaling. That's what we find. But of course, this is not a panacea also. You don't get rid of the vulnerability completely. You can reduce the HC first, or sorry, increase the HC first a little bit, reduce a bit error rate. We also study what else happens with voltage scaling, because voltage scaling affects other stuff, right? Like retention time, like activation latency, and we study that, and clearly it makes those other things worse. So there's this trade-off basically.
Reduce the pre-charge voltage, for instance, so less, like fewer hammers to be get pre-charge voltage.
Yeah, exactly. We couldn't control the pre-charge voltage, unfortunately, in this particular case. We could control only the word line activation voltage. But yes, if you could control them, I think you can also do that. So the paper is actually a lot of interesting data. We'd be happy to share it once it's ready. This is some, let's say, sneak peek for that. I think we need to do a lot more studies like this to understand RowHammer. Okay, let me talk about solutions, unless there are questions. So there's a lot of work that happened actually in 2020 and 2022, even still happening on solutions. I'll mention one of our solutions. We actually have some other solutions on the works. Let me give you the overall solution approaches. I think this is a more broader slide than earlier, but I showed you. More robust DRAM chips and or error correcting codes. I'm going to slash that. I don't think that's a good solution. Well, unless you come up with a like revolutionary DRAM technology that's low cost. Increase refresh rate, I'm going to slash that also across the board. You don't want that actually. With existing RowHammer counts, actually, it's extremely bad to increase the refresh rates to get rid of errors. Physical isolation, it's almost slashed in my view. Basically, the idea here is you somehow physically isolate victim rows from aggressor rows. This is very costly in terms of memory overhead, clearly. And people have shown that this is not perfectly doable, let's say. So there are some security guarantee issues also. The last two are the solution directions that have been explored a lot, and I think they have a lot of promise. Maybe combinations have promise. The fourth one is reactive refresh. And the idea is, Para is an example of this, probabilistic reactive refresh. But you can also have deterministic reactive refresh, figure out the access counts of different rows. And if you find that a row is getting closer to the hammer count, refresh adjacent rows. Graphene works this way, for example, with reasonably low overheads. Of course, overhead is in the eye of the beholder. So, okay, proactive throttling. Yeah.
Actually, to change the DRAM chip array to count to actually
Yeah. So you could do this in the memory controller. Memory controller, of course, easier.
Yeah.
If in the DRAM chip, yes, you do need to change, not the array. You need to add some auxiliary structures, counting structures. Like in graphene, they added some CAM circuitry. It's not very desirable, unfortunately. So overhead seems a bit low, but the complexity is actually still pretty high. So if you do it in the DRAM chip, I think complexities are going to be high. If you do it in the memory controller, I think you have a lot more freedom. But in the memory controller, you're limited by what you know about the DRAM and the interface. Well, okay, well, interface also a little bit, but you're on the DRAM chip, you're actually limited by the interface a lot more, right? In DDR4, for example, you don't have enough slack to actually induce things. You don't have, let's say, autonomy in the DRAM chip. Okay, proactive throttling has not been explored as much. I'm going to talk about one solution. This is actually interesting in my opinion, and I think we need to explore it more. The idea is here, can you detect whether some rows are being hammered and throttle accesses them? Meaning, don't try to refresh adjacent rows because you don't know which rows you're going to refresh, but throttle access to this row. Like blacklist them for some time. And I think this is actually a good solution direction, as I will show you in the results. I'm not suggesting this is the best because there are overheads associated with it also. We still need to find what's best. But the key is really this trade-off space, cost, power, performance, complexity, and we need to find a good point. I think we need to explore a lot of points and find a good point in the trade-off space to solve. So let me give you the idea of RowHammer relatively quickly. So there are two key challenges that we wanted to solve in this particular work. One is scalability. Have a scalable solution with worsening RowHammer vulnerability. As the RowHammer vulnerability becomes, let's say, 500 activates, can we still have the solution work at low overheads? Compatibility was the second one. Basically, can we have a solution in the memory controller without requiring any information from the DRAM chip? Like Para required adjacency information, right? We don't want that even. So that was our goal, basically. I already mentioned this, I think. And the key idea is very simple: selectively throttle memory accesses that may cause RowHammer bit flips. And there are two components to this. One is row blocker.
Throttle means just delay.
Throttle is delay, yeah, exactly. Delay enough so that the next activate will not cause a bit flip. Yeah. So we basically use Bloom filters to figure out row activation rates in the memory controller. And if a row is activated at a high rate, and it's not just one Bloom filter, there are two Bloom filters. You can read the paper for more detail. But if a row is activated at a high rate, you blacklist the row. Now, what does this mean? The memory controller doesn't schedule activations to those blacklisted rows for some time. Of course, you need to be careful about what is that time, right? And we have calculations in the paper that show this is by how much you should really not activate a particular row so that you don't get a bit flip. Again, this is based on the hammer count, which is the HC first value. So you really need to know that HC first value for a DRAM module, let's say. But a lot of solutions require that, unfortunately. Para also requires that for tuning. Yes.
What is this like for reading a large array, for instance? Would you install the entire array for just one row?
No, it's just that particular row access.
Yeah, but if you're reading the entire array, say consisting of say 100 rows, something like that.
But if you're not hammering all of them, right? Hopefully. So this happens.
When I say like array as a data structure array,
Okay.
not the memory array. So you're reading a
Sure.
Yeah.
So if you're reading a large array, you're doing one activate per row, right?
So
Then you will not be able to. This will not throttle you at all.
I see,
Yeah. This will throttle you only in the case where you're really activating one particular row. Hopefully that's not happening in benign applications. Unfortunately, we're getting to the point where we may be seeing it at the benign applications, right? Actually, when we did the study in 2012, early studies, we were asking the question, can we see it in benign applications? And the hammer counts at that time were 100,000 or so. There are no benign applications that we at least were exposed to. We did have some anecdotal evidence that there may be some benign applications that store a lock in the memory, and there are many threads accessing that lock, and they're all activating. I don't know, you could probably cook up some benign application also. But today, the hammer counts are on the order of 1,000. And there are some benign applications that are getting close to that number, basically. So, but hopefully, yeah, I think that's another question, in my opinion. Once RowHammer gets caused by benign applications, what do you do about it? That's something to study, probably.
Have you looked at benign application characterization?
Yeah, we did actually. We haven't published anything, but there are some applications. I mean, we didn't try to come up with the worst case benign applications also. There are some applications that can activate rows on the order of hundreds times. And that could be bad, clearly, right? Yeah. Okay. Okay, that's the idea, basically. Throttle activations target a blacklisted row. Basically, the key, and we have a security proof for this. And I think more recently, strong works actually have security proofs. No row can be activated at a high enough rate to induce bit flips. The second component is actually very interesting, I think. Here we can identify a thread that performs a RowHammer attack, meaning we can really like distinguish a benign versus non-benign thread, given the thresholds that we have, of course, at that time. And if you actually do this, you can throttle that thread completely, not just that particular row, but the entire thread, and you can report it to the operating system, say, operating system, do something with it because it's hammering my memory. So if you do this, we didn't do the operating system part, we throttled it. It greatly reduces the performance degradation and energy wasted of this attack, because there's this trade-off between security and quality of service, right? You may solve a security attack, but you may create a quality of service problem. This tries to solve the quality of service problem, like performance degradation problem. Okay, I will not bore you with all of these results, but if you have no RowHammer attack, BlockHammer's performance energy overheads are actually quite negligible, as you can see. As you can see over here, Para doesn't scale very well also at low hammer counts. So this purple curve over here is at low hammer count of 1,000. Para actually has a high performance degradation, 20% or so. And these are different metrics, if you will. Sorry, this is a very busy slide. The takeaway, I think I'm kind of writing them. These are some other solutions that are actually quite good also prior to BlockHammer, as we compare to. Now, BlockHammer's interesting part is it provides much higher performance and lower energy consumption than existing mechanisms when there's an attack going on also. I mean, this is not the common case, clearly, but when the attack is going on, you can actually detect it as well. Okay, so there's more to talk about in these, and I think the solutions need to cover many side attacks, etc. as well. If you're really interested, we have a characterization of the solutions until that time in this paper, kind of a framework to characterize different solutions, and we cover a lot of different ones. I'd be happy to talk about it separately. I think it's good to think about the solution space going into the future more. Okay, but I think my takeaway still doesn't change. We still need, I think BlockHammer is an example of an intelligent controller, much more intelligent than Para, but I think we need to do more in this direction. So there's a lot more about RowHammer in 2020, 22. I don't have time to cover. Actually, there in the security and privacy conference, IEEE security privacy, there was a session on RowHammer in 2020. Very interesting papers. Major security conferences usually have interesting things. OS conferences have interesting papers. And these are all very interesting papers. I think I'd recommend people take a look at it if they're interested. So this is another paper that shows that you could do this in JavaScript automatically. Again, in real chips that are supposed to be protected against RowHammer, building on trespass. Micro had some papers. So this is happening, I think, next week, IEEE Security and Privacy. And there are 3 papers on RowHammer that are quite interesting. I think both solution papers as well as attack papers, as you can see. Interesting that security conference are also publishing hardware solution papers today, which I think is nice. It used to be all software, right? These conferences. ASPLOS has some solution papers. HPCA has some papers. IRPS, Reliability Physics Symposium. More recently, we've also released a paper. We didn't publish it yet, but this is more of a position paper that kind of argues that we should be more transparent about the reliability characteristics of DRAM and have better cooperation between the DRAM and memory controllers. It's not just about RowHammer, this one. This one is actually about ECC, for example, also. If we are more transparent about what's happening in the ECC, in DRAM, we can actually build much better system-level solutions overall. Because Minesh is the first author of the paper. He graduated just recently. His work was on basically ECC, error correcting codes in DRAM. And he basically showed that you could reverse engineer what's going on underneath in DRAM chips also. With real DRAM chips, if a chip corrects an error, it could actually become a big problem in the system level because you don't know whether an error is corrected. It could actually cause this more errors, right? Because it's not able to correct the errors. Yeah, so that's actually interesting. And we also talk about it from a latency perspective also. If the chip provides more information about the latency reliability characteristics, you can do a lot more at the system level. Okay. So I think the interesting thing is a lot of these we can reverse engineer today, meaning a lot of the characteristics of chips we already know. If people have put the effort, as I showed you, you can learn about it. Why don't we actually have an interface that makes it nice for everyone to take advantage of it? Because reverse engineering is not nice in the sense that somebody needs to do it. And it's not a, let's say, sustainable method of improving the system, in my opinion. But if somebody specifies, okay, these are our characteristics, maybe the memory controllers in the system can be much better. Okay, maybe that's a dream, given the status of the DRAM versus, let's say, memory controller industry. Okay, so I think there's more to come. Do we have time to talk about some future challenges very quickly? Okay. Okay. Okay, so let's quickly cover some future challenges. I think there's a lot of interesting things that are going to come more. Clearly, there may be more errors slipping into the field in DRAM. RowHammer is a prime example, but retention errors may also be slipping into the field. Who knows? And I think there are a lot of other memories also, right, that we should be thinking about and hopefully not having problems like RowHammer in those memories going into the future. And I think I will repeat this as a parrot again. We need intelligent controllers, and hopefully they can avoid many failures and enable better scaling. I don't know exactly how to do everything, of course, but I think a 3-step methodology can be useful. We really want to understand what's going on. That's what we have been trying to do. Can we model and predict based on real device data and analysis? Can we understand these vulnerabilities? And can we basically fix them based on that, develop reliable metrics? Architecture is important, like principal architectures with security as key concern. Can we partition the duties across the stack nicely? Memory controller, memory, operating system, who knows what else? Clearly, we cannot give up performance and efficiency. And I think patchability in the field is really important, like our memory controllers having patchability or DRAM having some patchability would be really nice. I think DRAM, again, we're limited by the interface, and better interface also goes into this, in my opinion. Can we have somewhat of a better interface to the DRAM such that DRAM has some autonomy to do things? Today, DRAM doesn't have any autonomy to do things. Like it cannot even do refresh internally nicely. It has to get this command from the memory controller. But can DRAM somehow be a little bit more autonomous in the interface? That way we can partition the duties better across the stack, perhaps, right? Okay. Like inside the DRAM ECC. Yeah, exactly. So once you have the autonomy, then the question is what else do you expose to the other side? I think these are 2 different things. I agree. You don't want to be just autonomous and not inform everyone else in the world, right? Yeah. I think there needs to be still these 2 things at the same time. I agree with you. And design and test are really important, I think, especially online testing is still important because, again, over time, one of the things that we could not study, for example, aging behavior, right? Because this requires a lot of effort and a lot of time. How does RowHammer change with aging? I don't know basically the answer. But I think if we have a memory controller that does online testing, it will know the answer, or it can get some hint about the answer at least. And I think that's important for security, safety, reliability. If you have a self-driving car that's driving out in the field for 5 years and it has DRAM, it better test the DRAM once in a while, right? Okay, so okay, yeah, I think that's what we're getting at in this particular position paper also a little bit. Okay, so I mean, that's why we've been trying to understand what's going on with DRAM and flash, as you can see, and that's why we've been kind of writing the papers also. Let me go back to what I started with. This is the galloping Gertie. That's the name of the bridge. Basically, it's galloping because it was doing this actually for 6 months, and then it snapped, let's say. But this is, I mean, in this case, it was not that bad, but clearly there are cases where it was really bad. And we keep getting these bit flips. This is Minneapolis, this is Genoa. And if you were in Pittsburgh recently, I was actually there. You would have seen this. This is a bridge that I used to actually go on a lot. And it's fascinating that this bit flip happened. Now, there's a lot of aging also related to this. If you read stuff about it, you would see that it's certainly a reliability problem, right? That manifests itself as a safety and security problem. You wouldn't want to be on that bus at that time, as you can see. And there are actually interesting, beautiful pictures of this bridge over here. The good thing is it was not a fatal one, as opposed to some of the other ones earlier that I showed you. But yeah, so I think these are failures, right? So I think one downside with real infrastructure like this, real physical infrastructure is, it's not like computing. Computing is much softer, can be much softer. We can basically patch things, right? Much more easily. So I think we have a huge advantage. But computing is everywhere compared to the bridges, right? I think it's also interesting to kind of think about this bridge as a reliability problem. People have been building bridges for thousands of years. We still don't get it right, as you can see, because of, I mean, fundamentally, it's a reliability problem, and we cannot get everything about reliability right. So we should probably plan for it in a better way. I think patchability helps that in computing. Yes, sorry.
The sound still okay on online? Okay, yeah, I think it's okay.
Okay, it's okay. Yeah.
So there was a question from Bob, actually. He asked about does this problem also persist in HBM with, say, some processing in memory, for instance?
Oh, okay. That's a good question. I mean, we have not tested HBM, but there's no reason to think that this problem doesn't happen in HBM as well, because underlying DRAM technology is really the same in all of them. And I don't know of any work that has tested it, but I'm quite sure that it exists in HBM also. Maybe even worse, because your latencies are lower at HBM, especially if you're doing processing in memory, right? You're very close to the.
Is there also kind of the electric capacitive
Yeah.
effect in the vertical direction?
Yeah, that's one of the reasons why we want to actually do this on HBM, but we weren't able to. So I believe there is, but I don't think it's going to be as large as the coupling effect, that you have between the word lines. So that said, so what we did was on flash memory. Flash memory clearly is a totally different technology, and the read disturbance is different. But we did see layer-to-layer effects in flash memory. We have a paper in 2018, 2 papers in 2018, where we analyzed 3D flash memory, and there are a lot of interesting issues over there. Yeah. Okay, so I think in computing we can be much better. We can patch things basically. So we should be thinking from that toward that direction. And again, that's kind of what we argued in like 10 years ago also, in my opinion. So it's not us also. Industry is writing papers about it too. And I've kind of criticized the memory manufacturers a little bit, since they kind of deserved it, I think. But they also had the right direction, actually, in this particular paper. This is a paper by Samsung and Intel in 2014 in a memory forum that we organized. And I wish they had followed up on this, actually. So they basically talked about DRAM process scaling challenges. You can see refresh. They didn't talk about RowHammer at that time because it was not really publicly, let's say. We were working on it, and our paper appeared in the same conference their paper appeared. So they argued that they should really co-architect controls and DRAM together. And I think this was a great paper along the same lines that we have been arguing. I hope the industry follows up on this one. Yeah, I can only hope. Okay, let me give you some final thoughts on RowHammer, and I'm happy to take any questions anytime, actually. So this is the paper that I mentioned earlier. This was before RowHammer. This is from IEEE Security and Privacy 2003. It's a beautiful paper from Princeton, as you can see. And you may have seen it. Yeah. It's so basically what these folks did they essentially did what Google had shown with the Google native client with RowHammer. So they were able to induce memory errors, and they were able to.
He gave an applicant seminar here.
Oh, okay. At that time.
physically showing the-
Oh, he brought the computer. This setup basically. Yeah, exactly. This setup, you may have seen it if you've been around like Pradeep for some time. Yeah, clearly the way they induced memory errors was a little bit unconventional. Let's say they needed to induce these memory errors using this heat lamp over here. So it was very fascinating. They could take over the Java virtual machine.NET virtual machine, which Google essentially replicated with RowHammer in 2015 with the Project Zero attack that I mentioned. Now, of course, this is interesting, but this didn't really take security community up in arms. They didn't really build on this work as much as maybe they should have in retrospect, because I mean, who has this sort of physical access, right, to machines? So I think what RowHammer changed was enabled that error that they needed with a simple software, through simple software, right? As I showed you, right? With user level software, you can induce these attacks. So that's as a result, I think there's a lot of interesting research going on in hardware security because people figured out that real memory chips are vulnerable and they could do a lot of these fascinating attacks. Whereas if someone needs to have physical access, they don't want to do these attacks, right? They just wanted to induce these bit flips in software, basically. And yeah, so there, as a result, we see many new RowHammer attacks. Even right now, like this year, we see some attacks. I believe there's more to come as RowHammer is getting worse. It's worse at the device level. Of course, we'll have better system level solutions, hopefully. So the attackers will need to be, let's say, more creative to bypass. But actually, people have bypassed ECC as well. There are some beautiful papers that show how to do these RowHammer attacks by bypassing ECC. So it's very interesting. I think solutions are something we should really focus on. We need to do a lot more in this space, and hopefully there's more to come. I believe we need to be principled in this. Like we cannot just try to do things in the DRAM chip, in my opinion. Yeah. Like sometimes when I give this talk, people say this is just the manufacturer's problem. In a sense, it's true, but I think maybe this is a good opportunity to rethink our entire ecosystem of building systems, right? We've kind of thought of memory as like just memory. It's a memory manufacturer's problem, but given other trends also like memory-centric computation, perhaps memory should be more centric to the systems. Okay, I think this is my, let's say, thinking of RowHammer. General purpose hardware is fallible in a widespread manner, and this enabled people to think about other problems in hardware as well. So it's very interesting, I think, that two of the groups that worked heavily on RowHammer also went on to discover Meltdown and Spectre. Because it's kind of a mindset, right? Okay, what else is problematic in hardware, and can we find it? As a result, I think hardware security is very, very interesting in the otherwise software-dominated security community today. So hopefully there's more to come. Hopefully we can make our hardware a lot more safe, a lot more secure, a lot more reliable, so that we can really build things that we can depend our lives on, let's say, into the future. Okay, to conclude, memory reliability is reducing, and reliability issues open up new security vulnerabilities. These are very hard to defend against in the field. RowHammer is a prime example, and it's the first example that I know of a simple hardware failure mechanism that's causing a widespread system security vulnerability. If you know of some other example, I'd love to know. I couldn't find it so far. And I think its implications on system security research are tremendous and exciting. Of course, memory research as well. The bad news is RowHammer is getting worse, and there's no end in sight, let's say. If we get to 100 hammers causing a bit flip, I don't know, is that the end of DRAM scaling at that point? I'm not sure. I think the good news is at least we understand the problem much better. We have a lot more to do. We're now fully aware that these are problems. We're developing both attacks and solutions. I think both are good. And hopefully we're developing more principled models, methodologies, and solutions. And I think we need to do more. And again, I didn't cover a lot of works that are very, very interesting at different communities. This retrospective has that, and our lectures have actually a lot more as well. So I'll thank people who've been supporting our research, including folks at IBM through SRC. And most importantly, I should thank my students who have really done the collection of research over the last decade that I presented. And if you want to learn more about them, this is a newsletter, and this was our first in-person group meeting in December that we had. And finally, I think if you want to know a lot more information, we release a lot of information publicly online on our courses, actually. You can join them online as well if people are interested. We have a good online attendance on YouTube. people ask questions, provide feedback. We always welcome any kind of feedback. And thank you. I'm happy to ask, take more questions. Yeah, I'm happy to send them to the email thread, and you can share it. Yeah, everything over here is public, so there's no. I didn't say anything that I don't say in public.
I think you just broke the Watson.
Uh-oh.
205 slides.
Oh, wow, yeah.
Oh, really? Sorry. I hope I skipped some of them.
This is great. Are there any questions on the web? Please feel free to chime in.
Probably lunchtime.
Your 2014 ISCA paper.
Could you?
Was the very first
2014.
to the open public to announce this failure, right?
So yes, I mean, as far as we know, our paper was the first to really show that this is really doable in DRAM chips. Of course, read disturbance in DRAM has been studied, right? We're not the first one to study it. Like there's this IEDM, I think it's IEDM 92 paper by Rethinking. It's a very fundamental paper that studies crosstalk and DRAM read disturbance. And in the end, this is about crosstalk also, right? But the fact that you could actually do this in real DRAM chips was not, at least publicly, known until our ISCA paper. We did these studies starting from 2012, and we actually collaborated with Intel. And certainly, Intel filed some patents at the time that exposed it also that way. But those were patents, let's say, we actually referenced those patents in our paper. You can find references to all of those patents in our paper. Yeah.
Yeah, so as you said, by the time of 2013 or 14, actually only some suppliers and maybe Intel were aware of that failure mechanism, and they really tried to keep it secret. But what made you think to try this kind of failure mechanism?
What is the motivation?
What is the motivation? So, I mean, as I mentioned, we built this infrastructure for DRAM scaling issues, and we wanted to study retention times, and that was our first paper in 2013. But that was actually concurrent work with RowHammer, if I had to tell you the story. So, why did we study this? Certainly, so our flash work, the infrastructure that I showed you, actually, maybe I'll show again quickly. It predates our DRAM infrastructure. Where did I show it? Okay, this one. So this work, you can see that our first paper is in date 2012 that analyzes flash chips. This predates our DRAM infrastructure. We were very interested in memory scaling issues in general. I mean, I would have done it for PCM also, but I didn't have infrastructure for PCM and I couldn't build it, no question about that. But we were able to build the flash and DRAM infrastructures. And essentially, we wanted to understand all types of error mechanisms that we could think of. And retention errors are clearly important in both. But read disturb errors are actually very important in both also. So in our date paper, for example, over here in 2012, we talk about read disturb errors in flash. And that inspired us to study also read disturb errors in DRAM. So that was the main motivation. Memory scaling issues in general. And we did, so okay, that was the thing I wanted to mention. Our ISCA paper in 2013, that looks at retention time characterization. I think Pradeep was there at my presentation. I remember actually in Tel Aviv. That was published. That is concurrent work with our RowHammer work. It was published earlier because that was easier to, let's say, write. Our RowHammer paper was initially rejected from Micro in 2013. People didn't want to publish it. even in the ISCA, when we submitted, there were people who were very opposed to it, let's say. We got some strong rejects as well, but it was published in the end. So it took some time to publish it, let me put it that way. I don't know if that answers your question.
He was probably asking how did you get this idea of particular the RowHammer.
I see. Essentially read disturbance, right? I mean, Flash, for example, in our Flash work, we do the same thing. You keep hammering a page. Yes, the error mechanism is different because in Flash, when you need to hammer a page, you need to apply high voltage to the entire block. So the disturbance is even worse actually in Flash. But in DRAM also, there's no reason to think that it doesn't exist in DRAM. I think actually it's very fundamental. In a sense, there's nothing new in our paper, except the fact that there's a lot of analysis that people didn't know before. But fundamentally, it's about read disturbance, and all memories have read disturbance. Like if you give me a PCM, I will find the read disturbance also if it scales to enough, let's say, small enough technology nodes. But I'm curious to know your thoughts on like the memory industry at that time, since you mentioned that they knew about it, and I know that they know about it, but I'm curious because this was a good opportunity to develop solutions, right, at that time. Okay.
Thank you.
Sure.